Welcome. In this lecture in linear data analysis, we'll explore what we'll call the left transpose product of a matrix. That is, suppose that we have a matrix that has all real numbers and it has m rows and n columns, and we'll multiply this matrix on the left by its transpose. So let's suppose that the columns are linearly independent. And this would mean that the matrix is either square or it's a tall-thin matrix where it's full rank. So we've already explored this, and let's reiterate this. Let's call it B, and what we'll do is we'll refer to this as the matrix B sub V, and because we're going to calculate two symmetric matrices in this lecture, we'll call it B sub V, and we'll say that that equals A transpose A. And by the spectral theorem, this matrix is, because it's symmetric, it has a particular eigenvalue decomposition, eigenvector decomposition, and that is, it is some eigenvector basis V times its eigenvalue matrix times, and now it's not the inverse, it's specifically the transpose, because the columns of this will be an orthonormal basis for our M. So we can write V as the eigenvector basis. So this will be vector 1, vector 2, and so on until we have vector n. And in this case, the eigenvalue matrix will be, we can order these in any way we want by using permutation matrices. So we'll order them so that the largest one appears first. And so this will be lambda 1, lambda 2, and so on until we've written all of the eigenvalues that are in the matrix. Now, let's suppose a second thing. Let's suppose that the rank of this matrix is R, where that is not necessarily equal to n. So it will still have a spectral decomposition, and what will change is that in this case the eigenvalue matrix will have lambda 2 and so on, and then there will be some lambda r which is the last non-zero, and then we'll have zeros all the way down. So that will be the big difference, is that that for a rank deficient A transpose A is still symmetric. It's positive semi-definite because there are zero eigenvalues, and we can order the eigenvalues this way. So let's take an example that we've explored previously. And let's suppose that A is, first column is 1, minus 1, 1, 1, 1, 1. And from our previous work, we know that A transpose A is, we know that the diagonal entries are 3 and that the off-diagonal entries are 1. And we wrote the eigenvalues in a different order. Now I want to order the eigenvalues in decreasing values. So I'll write eigenvalue 1 as 4, and I'll write eigenvalue 2 as 2. And the eigenvectors because A is full rank and tall thin, the eigenvectors are an orthonormal basis. And for your convenience, what I'll do is I'll write these eigenvalues not in terms of unit norm, but in terms of simple human understandability. So I can write eigenvector 1 as proportional to 1, 1. And we can see quickly, so this is not the eigenvector of a rectangular matrix because that doesn't exist. It's the eigenvector of the left transpose. And if I take this matrix times 1, 1, I'll get 3 plus 1 is 4, 1 plus 3 is 4, I'll get the vector 4, 4, and sure enough, that is 4 times eigenvector 1. Likewise, eigenvector 2 is proportional to 1 minus 1. And by dividing each of these entries by the square root of 2, I would get an orthonormal basis for R2, which is what we expect from a symmetric positive definite matrix.